10.5 Faraday's law of induction and Lenz's law. Magnetic field can produce current. If currents make magnetic fields, it makes sense that it goes the other way around. The magnetic field must be moving to create the current. The current created is called an induced current. The EMF, which is also the voltage that causes the current, is called the induced EMF. So you can see down here we have a coil of wire and a bar magnet. Sitting still, nothing happening, we get zero current. If we move the bar magnet close to the coil, as it's moving closer to the coil, we get current. As we move the magnet away from the coil, we get current. So as long as we're moving the magnet closer or further away, we get current. Notice the current also ended up going the opposite direction when we move the magnet in the opposite direction. Another way we could create an EMF and an induced current is by changing the area. So if we took a round circle and stretched it out like this, that would actually create a current. In order to actually do the calculations, though, we need to think about something called magnetic flux. Magnetic flux, that's a capital Phi, equals the B field vector dot product with the area vector. Oh, I didn't know area had a vector. Yes, area does have a vector. If we get rid of the calculus, it's just the magnitude of the magnetic field times the area times cosine of phi. And again, phi is the angle between the magnetic field and the normal to the surface. Notice the normal to the surface is perpendicular right there. Normal means perpendicular, only it's more than that because you can make it to a curved surface too, where it'd be perpendicular to the tangent line to the surface. Anyway, and our angle phi is right there, the angle between the magnetic field and the normal. The magnetic flux is proportional to the number of field lines that pass through the surface. So think of a whole bunch of magnetic field lines going through the surface. The more field lines that go through the surface, the bigger the flux. Any change in magnetic flux causes a current to flow. So we can cause a current to flow by changing the B, the A, or the angle. For this example, a rectangle coil of wire has a length of 2 centimeters and a width of 3 centimeters. It's in a magnetic field. What is the magnetic flux through the coil? All right, so there's my coil of wire. And I have that the face is parallel to the magnetic field lines. So if we look at that, we see, oh, wait, there is no magnetic field lines going through that loop. Thus, the flux is 0. Otherwise, you could say, oh, the angle between the normal would be perpendicular to the loop. The angle there to the magnetic field is 90 degrees. Cosine of 90 degrees, when we plug everything in, is 0. You get 0. And the unit is Webers, or Tesla meter squared. So again, since no magnetic field lines pass through the coil, there is no magnetic flux. What is the flux if the angle between the face of the coil and the magnetic field is 60 degrees? All right, so I have my magnetic field going through my loop, and it's 60 degrees to the face of the loop. The formula is the angle goes to the normal to the loop. So I've drawn a blue little normal there. If it's 60 degrees to the face, it's the complement 30 degrees to the normal. So that the 30 plus the 60 make the 90 degrees. So our flux is BA cosine phi. Our B was the magnetic field. The A, it's a rectangular loop, so it's length times width. Change it to meters. And our angle is 30 degrees, again, because it has to go to the normal, perpendicular to the loop. And I gave you an angle that goes to the face of the loop. We want to the normal of the loop. Multiply together, 1.56 times 10 to the negative 6 Weavers.